Welcome welcome everyone. It is now 11:30, so let's start our session, our second session for today, which is on fault analysis on Post Quantum Cryptography II. And the first talk for this session is from MLWE to RLWE, a differential fault attack on randomized and deterministic dilithium. And the speaker will be Oliver Monchin, please.
Thanks a lot. So before starting, I would like to stress that this is a teamwork with all the co-authors at NXP, and that Mohamed has been leading this work. He's a student from us, and unfortunately was not able to make it here this year. So I will start with just a brief overview or a one-slider about what the attack is actually doing, and then we will elaborate a bit more. So yeah, also in the presentation, I will use some color codes. So everything that is green is known by the adversary. So the signature, the release signature, is given to the adversary, and what is in red is secret keys or ephemeral secret material. So the paper is about dilithium, and dilithium is based on MLWE. And in MLWE, you basically have a big public matrix here, where all the coefficients in there are polynomials, and then you multiply that with some secret key, you add another secret key, and then you end up with the public key, which of course is public. And the security there depends on multiple things, and among them, important security parameters are the size of the matrices and the size of the polynomial that live in that matrices. Of course, we are at CHES, so we are a bit talking about physical attacks. And here we'll be talking about fault injection, where basically with fault injection, you force the target to manipulate corrupted data, and maybe the target will release that corrupted data. We use that technique to reduce the hardness of the MLWE problem to ring LWE, where it looks like something like this, where you have here just a public polynomial. It's equal a polynomial times a secret polynomial plus another one. And it looks like a bit simpler than the big equation above. And we use that to mount key recovery. Why are we able to recover key recovery from that ring LWE instance? Is basically because the polynomial have a size that are dimensioned to be used in MLWE, where you have big matrices, and here there is no matrices. So the polynomials are too short to be using a ring LWE instance. So it means that the problem is less hard, and we are able to use state-of-the-art lattice solving techniques to recover the full secret key. Okay, so now it's the outline of the presentation. So I will first describe dilithium signature, and especially the signing, how signing works in dilithium, and that has already been done in the previous session, but I will recall that. Then I will give a high-level overview of what the attack is about, and essentially where we need to insert the fault, and then how we exploit the resulting faulty signature to get back to secret keys. Then I will talk about how the fact that the dilithium is based on Fiat-Shamir support impact on the number of faults that needs to be actually inserted in the device. And then I will just briefly explain some extra content that is in the paper. Some remarks is that in dilithium, there is some public key compression that makes the attack still applicable, but a bit more harder. And for this presentation, we will completely omit that part, but the details are in the paper. Also, all the equation and figures that I will show are just here for educational purposes. And again, if you want more details, go and check the paper. And also something important that is in the title is that the attack applies to all dilithium variants. Okay, so now some overview of the attack, and for that we start with dilithium. So what is dilithium? Essentially, you start by generating a seed here. So you generate a mask here, Y, where you generate it from expand mask, which is a function that will take a secret seed and a public counter kappa. And from a PRNG, you will generate Y. Then from that Y, you can generate challenge C, and that takes into account the message and the public matrix. And then you generate a signature by multiplying the challenge with the secret key S1, and then you add Y and you get the signature. As outlined in the previous talk, maybe that signature is a bit too large and will reveal secret information on S1. So if the signature is too large, you just repeat the process. So you increase the counter. That means that you will get a new Y and then a new challenge, and then you just start over the process. And you continue until the signature is small enough, and then you can release it. Okay, and the fault that we will perform is a bit as in the previous talk, is on the generation of Y. And for now, we will completely omit the fact that there is fiat shamir with abort in that construction. So we will just focus on the last iteration of the process where the signature is actually released. Yeah. Okay, so how does it work actually? Ah. Okay, that's okay. Okay, so here, how do we generate one polynomial in the signature is essentially, so this is one polynomial in the signature. You get it from expand mask, where you put the seed, then you put some public data, and then you get S times C times S1 and the first polynomial in S1. And from that, you get the signature, and this is called Y. So you do that for the first polynomial. Then you can do it for the second polynomial in signature. And the only difference is that here you add the second polynomial in S1, but you also increment the public counter by 1. So this is correct execution. And what you can do as an adversary is to say, okay, what happened now if I just skip the increment here and I just make sure that this never occurs? So I will end up in the signature here, Z0 and Z1, that both embeds the first polynomial in Y, and the first polynomial in Y is embedded in both signature polynomials. And this is the faulty execution. So, okay, that's skipping an increment. I guess most of you know how we can do that. So if you look at the disassembled code at some point in the expand mask, you will end up with having a next instruction that's the increment. And basically, you can skip that instruction or insert any fault that will make that instruction ineffective. And that's where we can insert a fault. Okay, so I described what fault we need to do, where we can just insert it. So let's look at a bit of how we can exploit it. So this is just what I explained before. So you get a first signature, then you get the adversary gets 2 polynomials in the signature Z. And what it can do is just compute the difference between them such that it cancels out the Y0 on both sides. And you can do that for a second signature where you do not skip the first increment, but you skip the second increment. So you get Y1 twice, and then you again compute the difference. Okay, you can do that for a third signature. And in the end, what you end up with is, okay, you have a system of equation. You have 3 equations and you have 4 unknowns. So basically the 4 unknowns are the 4 polynomials in S1 ranging from S10 to S13. And it means that with standard linear algebra that you can express all the polynomial in S1 by S10. So essentially you can do something like this, where the public data is just summarized here with 1 lambda. So that simplifies the thing. And then you can just take these 3 equations, plug them into a Delicium MLW instance. Then you have to simplify a bit. Again, go and check the paper for that. And you end up with a big equation like that, which actually is a ring LWE instance where all this sums up into one polynomial P, which is known by the adversary because it's only composed of public data here. Then you have the same for A, and then S10 and S20. And all these are just polynomials. Okay, so that's how we move from MLWE to RLWE by inserting 3 faults, where you have 4, where you had for polynomial in the secret key. Okay, so of course now we have reduced the MLW to RLWE, and the question we ask ourselves, of course, is okay, how are the problems and can we solve it essentially? So for that we use public tool, which was published in 2020 at Crypto by DDGR. So in the rest of the talk, I will mention that as DDGR. Okay, and by using their tool, we just estimate what's the hardness of the dilithium MLWE instance without fault injected. So what you can see here is here the parameter set, so level 2, level 3, level 5. And then what's important is to see here is the beta, which is how hard the problem is. Okay, that's without any fault, so the standard MLW instance. But what you can do is just insert L-1 fault, where L is the number of polynomial in S1. You reduce to RLWE, as I just explained before, and then you end up with something like this. So let's say for level 2, we just need to insert 3 faults, and then the beta drops from 434 to 62. And using the DDGR framework running on a standard desktop, you are able to recover the secret keys within 40 hours on average. Okay, the same goes for level 5, and just with this, we were not able to completely attack parameter, the level 3 parameter set. So that's why we search for some improvements. The question we ask ourselves is kind of what can we do more with the faulty signature? So yeah, that's the question we ask ourselves. And can we have something that will help out for the lattice reduction techniques? So we did something very simple but quite effective. So essentially, here you have the system of equation I just described before. And this is polynomials, and everything is just addition. So you can express that as addition coefficient-wise. And on the right here, you just rewrite n system of equation, which are just like this. And what's important to note is that the coefficient is S1 are quite small. So what you can do is to search for unique solution for S1, for all the coefficients S1 independently. And because they are small, they are super easy to enumerate. So on average, with just that technique, we were able to recover a large portion of the secret key, of the unknown secret key coefficient into S1. And then we can just plug that into the DDGR framework. Yeah. So how does this impact the attack? Essentially, so that's the table I just shown before. But now what we do more is to just insert is to do the enumeration, sorry, and then use these ints within the DDGR framework, and you end up with something like this, where you even drop the beta even more. So here we were able to break all the parameter sets within 15 hours up to 23 hours, and that succeeded with success rate 100%, and we did that for 10 independent experiments. Okay, so that's how the attack works if you get the faulty signature. But then Fiat-Shamir-Roussabord came into place. Okay, so the thing is that with Fiat-Shamir-Roussabord, our says is that you have this process that you repeat, and yeah, it continues until the signature is in the correct range. But as an adversary, you would like just to insert a false one. And from that fault, you would like to get the faulty signature, of course, because otherwise you just get a legit signature if it's not reached during that iteration. So something which we noticed is that, okay, the signature here, when the fault is injected, has a particular form, especially if you take like the first polynomial and the second polynomial, you subtract them, they have a particularly small norm, so you can know, you insert a fault, you get the signature, you can say, okay, this is the faulty signature, I'm almost sure of it. And then the question is, when is it better to insert the fault So for randomized dilithium, what we discovered is that it's just better to fold the first iteration of the process because there is no other way to know which one is the best. So just fold the first one. And for the deterministic version of dilithium, what you can do is just start a legit signature. You will have that loop will iterate. That loop will iterate, and at some point you will release the signature. And what you can do is just using timing and get, okay, I will insert the fold during the last iteration. Okay. So now the question is, okay, I know that I can insert fold, but I'm not sure that I will get the faulty signature. So essentially, how many folds do I actually need to inject to be able to recover the key? And the strict requirement is that you need to obtain L-1 faulty signatures. So we did graph like this. On the x-axis, you have the number of folds that you actually inject in the device. And on the y-axis, you have the probability that you obtain enough faulty signature to get back to the secret key by using what I described before. Okay, so we have a graph like this, where we have for randomized dilithium for all the parameter sets, and same for the deterministic dilithium. What we can see is already that deterministic dilithium, you require less fault than randomized dilithium. And something that we notice also from here is that as soon as you insert L-1 faults already here, there is a chance that all the fault you inserted will give you the faulty signature that you can exploit to mount the reduction. And that's here. But okay, that's maybe for an evaluator, it's cool because you say as soon as the guy is able to insert L-1 fault, maybe get the key. But for an adversary point of view, it's not super friendly because if you insert L-1 fault, you are not fully sure you will get the key. So you can read this graph in another way. You can say, okay, if I inserting 15 faults and I'm targeting randomized dilithium level 2, I will have 80% chance of recovering the and here is the numbers of average traces, average faults you need to insert to get back to the secret key. So it ranges from 7 to 22 traces. Okay, so that's what I wanted to talk during this presentation. Maybe some interesting points is that the attack, we can prevent it. So in the paper, we introduce a countermeasure that is just looking at the structure within the release signature to detect if a fault was injected. So a bit as I explained before, that the adversary is able to look at the norm between two differences of 2 polynomial in the release signature. The chip can actually do the same to detect the faults. And what you can also do is just recompute the last, you can also just recompute the last iteration in the process and verify that the release signature are the same. Okay, and I mentioned also in the introduction that there is public key compression in dilithium and that we omitted here, though. So the attack remains the same, but the beta is a bit increased. So here is the different beta we had, which means it's harder, but still significantly less harder than for the standard dilithium instance. And we were able to break dilithium level 5 completely, but not the other parameters. Okay, so a small summary. So we presented a new differential fault attack on MLWE. This applies to both deterministic and randomized dilithium. And the core of the attack is really to take the MLWE instance and map that to a ring LWE. The resulting instance can be broken practically either by using this small enumeration technique I use or just without it. And the attack is kind of efficient because you need more or less 10 faults to get back the secret key with good probability. And we propose new countermeasures. So that's it for me. I'm happy to take any question now.
Thank you very much for very interesting talks, and we have plenty of time for questions.
Hi, thanks for the talk. So you mentioned 10 faults are enough to perform the attack.
Yeah.
But also you mentioned that the fault is very specific, right? So you need to skip an instruction somewhere. So what if you inject another kind of fault? How easy it is to filter out the faults that are not useful for you and focus on the ones that you can use for attack?
I think as soon as you have that particular structure I mentioned, then you will be able to mount the attack. But now, how likely is it that another kind of fault will lead to that structure? I don't really know. But let's say something that you could do is just skip the function call such that the vector, I mean, the polynomial in Y won't, I mean, let's say if you have a buffer, you do unspend mask once, and then you have the polynomial you process once, and then you do the same a second time. But I mean, if you fill the same buffer the second time you call it, and you don't, and you do not, and you skip that, then in the end you will end up with having twice the same polynomial. Why? That's an idea, but I think we did not spend a lot of time in thinking what practical fault will lead to that, but more focusing on what, if we have that, what we can do with it.
Okay, thank you.
Are there any more questions for the speaker? Then I'll just ask one question. So towards the end, you briefly mentioned about countermeasures. Could you please comment what would be the impact of the performance if we add those countermeasures?
Yeah, so the countermeasure is just checking that you have that special form in the signature. So it's relatively easy to do. And depending on how you parameterize it, you can detect the fault with a very high probability with almost negligible cost. So I think that's fairly good countermeasure, but it just protects against that kind of attack, which is the drawback of the countermeasure.
Thank you very much. That sounds very interesting. Okay, last chance. Are there any questions? If not, then let's thank the speaker again. Just while the second speaker is setting up. So if you do have questions and if you are shy, you can also log into Zoom and you can type your questions there and I will read it out here. Okay, are you ready? Okay, let's move to the second speaker of our session for today with the title, Filling the Twindle Constants Fault Injection Analysis on the Number Theory Transform. And the speaker is Prasanna Ravi, please.
Hello, everyone. Thank you for the introduction. I'm Prasanna Ravi from Nanyang Technological University, Singapore. This work was jointly done with Bolinian, Shivam Basin, Anupam Chattopadhyay, and Fanjang. So in this work, in this talk, I'll be presenting a work on performing a practical fault attack targeting the number theory transform, which is a critical subblock in schemes like Kyber and dilithium. So this is the simple outline of my talk. I'll start with a bit of motivation, followed by explaining the attack methodologies on Kyber, as well as dilithium, followed by conclusion. So we know that Kyber and dilithium are the schemes that were selected for standardization at the end of round 3. And both of these schemes share several common features. So firstly, their hardness is derived from the module learning the error problem. And they operate over very similar polynomial rings, leading to similar polynomial arithmetic operations. So as a result, they also share several common building blocks. And the common building blocks are the central binomial distribution sampler, as well as the number theoretic transform. So if one is able to find an implementation weakness in any of these building blocks, then it will basically simultaneously affect both of these schemes. So when we looked at literature, we identified that the number theoretic transform in particular has been targeted by several prior side channel attacks. But to our knowledge, there was no fault attack that has been performed targeting this particular block. So this was something that interested us. And Hence, in this work, we try to bridge the gap by proposing the first practical fault attack on the number theoretic transform. And the main identification was that we identified a single point of failure in almost all open source entity implementations for the ARM Cortex-M4 microcontroller. And this particular fault vulnerability allowed us to zeroize all the twiddle constants, which are actually constants that are used in the entity computation with just a single fault. And this ensures that the entropy of the sensitive inputs are significantly reduced, leading to practical attacks on Kyber and dilithium. And we experimentally validated this attack using electromagnetic fault injection that works with a very, very high repeatability. And we also show that our attacks are able to bypass several fault injection countermeasures proposed for both Kyber and dilithium. So I'll start by explaining a fault attack on Kyber, particularly focusing on the key generation procedure, and the same methodology can also be adapted to the encapsulation procedure as well. So the main intent of a fault attacker to target the key generation procedure is to generate a faulty public key from which the attacker can easily solve for the secret key, or an attacker can also do the other way around. He can also inject faults on the secret key to potentially reduce the entropy of the secret key, which can be easily guessed by the attacker, right? So this is the main intent of the attacker. So let's look at how the key generation procedure in Kyber works. So yes, you essentially want to sample three components. So you have A, which is sampled from a uniform distribution, a large uniform distribution. You want to sample S and E, where S is the secret and E is the error. And both S and E are sampled from a very narrow centered binomial distribution. So you simply compute the product A times S and you add it with E, and A and T basically form your public key while S is your secret key, right? So the operation that we want to target is the multiplication operation of A times S. And this multiplication operation is done using the number theoretic transform in the following manner. So you take A, you basically transform A into A prime using the number theoretic transform. You do the same for S. You do a pointwise multiplication, and then you do an inverse entity operation to compute A times S, right? So now let's look at how the entity operation works. So the entity operation, so the entity operation basically contains, or rather it uses a certain set of pre-computed constants, which we refer to as the twiddle constants. And if you look at a bare metal software implementation on an ARM Cortex-M4 like device, you can actually observe that these twiddle constants are actually stored in the flash memory as part of the firmware binary, right? So now let's look at how these twiddle constants are actually manipulated in such implementations. And mind you that this is the implementation style that's used in all open source assembly optimized implementations of entity using Kyber and dilithium, right? So the twiddle constants are obviously stored in the flash memory at some memory location, which is mentioned here as TW_address, and the address itself is actually present in the flash memory. So if the CPU wants to use these twiddle constants for computation, the CPU will first start by fetching the twiddle address, which is residing at a certain memory location, and subsequently all the addresses of the other constants are simply calculated by adding offsets to this base address. So essentially you have a single base address, and you're simply adding offsets to compute the addresses for the other twiddle constants. So the main observation is that you have a base address to calculate address for all the constants. And the question is, can the attacker actually fault the base address to basically corrupt the twiddle constants? So, and why is faulting the base address easy? It's because this base address is actually fetched from the flash memory to the CPU. And there is actually a prior work which shows that it's actually very easy to inject bit set and bit reset faults on data that's transferred from the flash memory. And this you can do with very good precision. So let's assume that the attacker is able to inject a fault in order to corrupt the base address to point to a different location, which potentially has a lot of zeros. In this way, with just a single fault, you ensure that the entire twiddle factor array is actually zeroized. So this is the implementation vulnerability that we want to target through fault attacks. So yeah, essentially with a single fault, the attacker can zeroize the entire twiddle factor array. And also we did an experiment where we wanted to fetch the twiddle factor array from random memory locations in the entire address space. And we identified that 25% of the times we were able to fetch an entire zero for the twiddle factor array. So there is a large possibility that you can fault to a value that can fetch you an entire zero twiddle factor array. So this is actually a illustration of the assembly implementation. Here you basically see that the twiddle pointer is first loaded from flash, and all the subsequent twiddle addresses are actually calculated from this twiddle pointer. So just faulting this twiddle pointer at the start is sufficient to corrupt all the twiddle addresses, basically. So now what happens when you inject a fault? Basically, upon injecting a fault where you zeroize the entire twiddle factor array, the entropy of the input reduces by half in every entity layer. So just to give you an idea, let's say you have an 8 input entity, which has 8 coefficients from S0 to S7. So if you zeroize the twiddle array, what happens is the entity output is nothing but the first 2 elements S0, S1, which is just repeated n by 2 times. So you see that the output of the entity operation, the entropy is drastically reduced. And if you actually compute the product of A times S on this fault using the faulty entity operation, you basically see that the actual secret that's used is S0, S1, and all the other coefficients are actually zeros. So there are only 2 non-zero coefficients for the secret, and all the other coefficients are actually zeros. So you essentially end up with a valid secret, but this secret has a very low entropy. So Kyber uses an incomplete entity, so you end up with 2 non-zero coefficients at the entity output, or rather 2 non-zero coefficients for the faulty secret. But in case of dilithium, which uses a complete entity, you only have a single non-zero coefficient, and all the other secret coefficients are actually zeros. So the entropy of the secret is drastically reduced. So you also what you would identify is that both Kyber and dilithium are based on the module LW problem, which means that you have k polynomials in your secret. So essentially there are k entity operations that are happening. And but what we experimentally identified is that faulting one single entity is sufficient, and the fault actually propagates to all the different entities. And one reason that we think is that the faulty twiddle pointer is actually cached and reused for all the k-1 entity operations. So a single fault is actually sufficient to affect all the k entity operations, which is actually an interesting observation. So now you are essentially ending up with a very low entropy secret key, which is also valid, which also generates a valid public key. And an interesting property in Kyber is that Kyber uses the same faulty secret also in the decapsulation procedure. So just injecting a fault in the key generation procedure is actually sufficient in order to basically create a valid key exchange. So the key exchange is valid, and this results in a valid attack. And we also validated this attack on masked implementations, where repeating the same fault on all the shares basically results in the same attack. So now I'll move on to the fault injection attack on dilithium, where we have 2 types of attacks. One is the signature forgery attacks, and also attacks on the verification procedure to bypass verification. So I'll start with our attack on the signing procedure. So I think Olivia gave a very nice background on how dilithium signing works. So I'll probably not go into too much into explaining how dilithium signing works. So essentially, let's start with understanding how the fault attack on the deterministic variant works. Then I'll talk about the attack on the probabilistic variant as well. So in the deterministic variant, you are basically generating a nonce from the message. And you simply want to use the nonce to generate a challenge, and you multiply the challenge with the secret, and you add the nonce to this product, and you perform several rejection checks, and then you basically output the signature, right? So what we want to do is we want to basically inject a fault in this particular polynomial multiplication operation, which is the multiplication of the secret with the challenge. So because the attacker can choose the message, the attacker can choose a message such that the first coefficient of C is actually 0. So if you zeroize the twiddle constants on entity of C, you end up with the entity of C with having an all zero value. What it means is that the product of S times C is effectively zero. And because of that, your signature is nothing but the nonce itself. And obviously, we know that leaking the nonce results in a devastating attack on dilithium. And what an attacker can do is attacker can perform a differential fault attack, right? So the attacker can generate a valid signature, and the attacker can, for the same message, the attacker can generate a faulty signature with a single fault on the entity operation of the challenge. And with just subtracting the valid signature from the faulty signature, you can basically recover the entire secret key with just a single. So now let's look at the attack on the randomized variant. And here it's interesting because this attack is only applicable on a particular implementation variant of the randomized dilithium signing procedure. So the attack only applies if the signature component Z is actually computed in the entity domain, but the original specification of dilithium, or rather the existing implementations of dilithium, always compute, they don't follow this approach. So, but we found that this particular implementation variant consumes lesser amount of memory. So it's definitely interesting for a designer to go for this approach to calculate the signature component. So if dilithium is implemented in this way, then what happens is the attacker can actually target the entity on the nonce itself, which basically results in a very low entropy nonce. And obviously using a nonce with very low entropy unmasks the coefficients of S times C, where S is the secret and C is the challenge. And this again can lead to easy key recovery through Gaussian elimination with just a single fault. So this is our attack on the randomized variant. And now I'm going to talk about the fault attack on the verification procedure. So to our knowledge, there has not been a practical fault attack demonstrated on the verification procedure to our knowledge. So this is the first attack that does a practical fault attack on the verification procedure of dilithium. So this is how the dilithium verification procedure works. So you have the signature components Z and C and the message M. You have two public key components, PK0 and PK1. So you simply multiply Z with PK0, you multiply the challenge with PK1. And essentially, the whole point of the verification procedure is to recompute the challenge and compare the recomputed challenge with the received challenge. And if they compare well, then you say the signature passes, else you say that the signature verification fails, right? So the most obvious target for to bypass verification is the comparison operation. So we would know that the designer would fortify this particular operation with redundancy-based countermeasures. So the interesting question to ask is, are there any other operations in the verification procedure that can be used to bypass verification? And turns out that the answer is yes. So what the attacker can do is the attacker can actually target the entity of the challenge itself. And the idea is that the attacker chooses a message and a random Z prime and simply computes a bad challenge as follows, which is simply hashing A, which is the public constant of the key, public key followed by Z prime and PK0. And another property that needs to be adhered to is basically that the first coefficient of the bad challenge has to be 0. So if the attacker is able to fault the entity, then this ensures that the product of C with PK1 becomes 0. And because of that, the recomputed challenge is nothing but the received challenge. And this will ensure that the verification passes successfully. So you here again, a single fault on the verification procedure can basically bypass verification, and the attacker can actually forge signatures for any message of his choice. So we now on to the experimental evaluation part. So we perform practical experiments using electromagnetic fault injection, and our target is the optimized implementations of both Kyber and dilithium from the PKM4 library, and we implemented this on the ARM Cortex M4 microcontroller. So we were able to actually achieve 100% fault repeatability using several fault parameters, and very repeatable faults could be achieved because we are essentially targeting data transfer from the flash memory to the registers, and any data that's transferred from the flash memory is much more accessible to fault injection, especially using EMFI. So we were able to achieve faults with 100% repeatability for several parameters. And our attack is also able to bypass several fault countermeasures that were proposed for Kyber and dilithium in prior works. I don't have details in the slide, but for more information, you can definitely refer to the paper. So these are some of the results when targeting Kyber. So the first plot that you see here is the number of faults versus time. And here you can see that about 10 nanoseconds of the time window is actually available for an attacker to actually inject the zeroization faults. And here, this is the spatial location on the chip where we were able to inject the fault. And this is basically the cartography where there are several yellow blocks, which denote that we were at all these locations, we were able to achieve a fault with 100% repeatability. And these are results for the key generation procedure, and these are results for the encapsulation procedure. And similarly, these are results for dilithium signing, both the deterministic and probabilistic variant. And these are results for the verification procedure as well. So in all of our experiments, we observed that this fault is highly repeatable, and hence we were able to perform practical fault attacks on both Kyber and dilithium. So now moving on to countermeasures. So because the vulnerability that we identified is an implementation level vulnerability, we need to come up with implementation level countermeasures to protect against this attack. So the first countermeasure that we propose is to perform a sanity check on the Twiddle constants. So we know that Twiddle constants are nothing but the nth root of unity. And these nth root of unity basically has nice arithmetic properties. So you can actually perform some sanity checks before you use these Twiddle constants for the entity computation. So the second countermeasure would be to perform sanity check on the entity outputs itself, because we know that upon injecting the fault, the entity outputs entropy is drastically reduced. So before using the entity output for further computations, you can definitely try to perform some entropy checks or sanity checks on the entity outputs. And the third countermeasure would be to simply remove the single point of failure by ensuring that you do not rely on a single base address to access the entire Twiddle constant array. So this will also easily prevent. It will make the attack more harder, obviously, but it probably wouldn't really prevent the attack, as the attacker would just need to inject a more number of faults. But this can definitely be used as a mitigation technique against the attack. So to conclude, we have presented the first practical fault attack on the number theory transform applicable to both Kyber and dilithium. And the main idea was to zeroize the entire Twiddle factor array with a single fault. And we observed this fault is repeatable on almost all open source assembly optimized entity implementations for Kyber and dilithium. And we were able to practically validate the attack using electromagnetic fault injection on the ARM Cortex M4 microcontroller. And we were able to also show that several fault countermeasures can actually be bypassed. So dedicated countermeasures to protect the entity operation is necessary to defeat our attack. So yeah, thank you. And if you have any questions, please do let me know. And thank you for your attention.
Thank you very much for your presentation. Are there any questions? Yes.
So I have multiple questions, but let's go for the first one and then see if there's other people. So you're faulting the base address of the Twiddle factor table. Why, or is it more difficult to fault the base address of, for example, the Y vector, or A?
Yeah. So to answer your question, basically the Twiddle constants are applicability constants. So they are stored in the flash memory, and the starting address of the Twiddle constant array is also present as part of the flash memory. So that's actually fetched from the flash memory, and this makes this more accessible to injecting faults. But we observed that the base addresses for the other, I would say, variables like Y or A, for instance, they don't follow this behavior. Actually, they are dynamically computed, and the fact that the variables that you're talking about are also used at several other operations in the computation. So the attacker has to always inject faults at all the places to ensure that it results, so the attacker can do an actual attack. But here, that's not really the case. So I would say that faulting the Twiddle constants is much more easier.
Back there, there's a question.
My question is about the sanity check. So what might be leaking if we only check for the entropy of Twiddle factors? So instead of checking, so we simply skip the check of arithmetic property of a constant. So, and we only need to check if the constant load from memory are non-zero value within plus minus q/2. What might be leaking for this kind of protection?
Sorry, if I understand your question correctly, so you asked that it's possible to skip the check as well, is it?
Yeah, so if I can go to the countermeasure page. Yeah, so I'm talking about countermeasure 1.
Yeah.
But I want to skip the first point.
Yeah.
I want to check I want to skip the check for arithmetic property of Twiddle factors. I want to only check the entropy. What might be leaking if I only do so?
Yeah. So if you're coming up with countermeasures that involve sanity checks and so on, so obviously a trivial way to attack this is to perform a double fault attack. So you fault the countermeasure as well as fault the actual operation. So obviously you'll have to implement it in such a way that you adopt enough amount of redundancy so that the attack can be defeated. So I hope I answered your question correctly. If not, we can definitely take the discussion offline. Yeah. Thank you.
We do still have time for questions. Are there more questions?
So I'm not sure when it was, but I think I read slide 19. You said that delaying the inverse entity,
Mhm.
like doing the addition before the inverse entity, gets you a lower memory usage.
Yeah.
Why is that?
Because if you're delaying the inverse entity computation, then you do not have to store both n and the entity of n. You can just override the entity of n over the same variable that holds n. So you are not using n as well as the entity of n. So in that way, you are actually saving some memory space.
So because it's an in-place entity.
Yeah, exactly. So this allows for an in-place computation, which reduces memory usage. Yeah.
Are there any other questions? If not, then let's thank the speaker again.
Thank you very much. Thank you very much.
So let's welcome to the last talk for this session with the title Belief Propagation Meets Lattice Reduction, Security Estimates for Error Tolerant Key Recovery from Decryption Error. And the speaker is Julius Himmeley, please. And while we are waiting for the slides, if you have questions and you don't want to raise your hand, you can log into Zoom and you can put your questions there. Okay, now the slides are ready, please.
This talk is about security estimates for error-tolerant key recovery from decryption errors. I'm Julius Hermelink. This is joint work with Erik Mortensen, Simona Zangiska, Peter Pessel, and Gabi Treo-Rodosek. The context of our work are certain attacks, an attack strategy on Kyber that target the error correction using a chosen ciphertext attack and either a fault attack or a side channel analysis. Kyber as an MLWE scheme requires an error correction that recovers the message from noisy polynomial coefficients. This happens during the decryption. So Kyber is built using an FO transform. And This means we have a decapsulation, and this decapsulation not only decrypts the message, but also re-encrypts it to compare the resulting ciphertext to the submitted ciphertext. And during this decryption, there's an error correction, and previously several attacks have targeted this error correction. The attack strategy here works as follows. So on the left side here, we have the decapsulation. And what the attacker first does is generate a ciphertext by honestly encrypting a message to a ciphertext. Then in the second step, a small error is added to one coefficient. And this small error potentially causes a decryption failure during the decryption. So the ciphertext is then submitted to the device. The device first stores the ciphertext in memory, performs the decryption. This potentially fails and outputs a different message. And if the attacker can observe this, then the attacker gains information about the secret key, about the error term, and thereby about the secret key. So this means if an attacker can submit a faulty ciphertext and then observe whether the ciphertext does actually cause a failure, then they gain information. And in Kyber, these attacks, they all retrieve inequalities over the secret key. So two previous examples, these two works have identified leakage in the comparison operation. That means, again, those attacks encrypt the message to a ciphertext, then add a small error to one coefficient, submit the ciphertext to the device. The device stores this, decrypts the ciphertext. This potentially outputs a different message now. And whether a different message is outputted really depends on the secret key, on the error term, and this in turn depends on the secret key. The device then re-encrypts the ciphertext, the message to a ciphertext, and then compares to both the ciphertext that was submitted and the re-encrypted ciphertext. And if there's leakage in the comparison operation, then the attacker gains information. And in Kyber, this comes in the form of inequality that is linear in the secret key. So in the inequality on the right side here, E and S are the secrets, and the other terms are known to the attacker. So we have an inequality that is linear over the secret key. Another example have been two fault attacks that exploit a similar principle. Again, the attacker generates a ciphertext, honestly encrypts the message to a ciphertext, and adds a small error to one coefficient. The ciphertext is being submitted. The device stores this, decrypts the manipulated ciphertext. And then during this decryption and re-encryption step, what the attacker does is they fault the storage. So they fault the ciphertext or they fault the re-encrypted ciphertext, and thereby they can force the device to decrypt the manipulated ciphertext, but compare against the original honestly generated ciphertext. So this means the decapsulation will only succeed if and only if first the fault works and no decryption failure happens. This should be noted that the small error in one coefficient in the compressed ciphertext only makes the ciphertext differ by a single bit, or potentially more bits, but the attacker can choose it in such a way that it's a single bit. Then this comparison succeeds if no decryption failure happens and the fault succeeded, fault the correct value. In all other cases, it fails. So if the attacker can observe the outcome of the decapsulation, they again obtain such an inequality. Additionally, has also been an attack that just targets the error correction using a fault and doesn't use a chosen ciphertext. So if we look at these kinds of attacks, then this is really a general attack strategy and not just a single attack, and it can be made use of using either a fault or side channel leakage in several different locations. And all of these attacks, they all retrieve the same kind of information in form of inequalities. Those inequalities are not trivial to solve. And if we want to carry out those attacks in practice, we need a key recovery method from those inequalities. So if you want to obtain the secret key from those inequalities, we need a key recovery method. And if we want to understand these attacks, in particular, if we have countermeasures in place, in the presence of countermeasures, then we need to know how inequalities translate to a certain security level. Previously, several methods for full key recovery in practice have been presented. So there exist several methods. They are all based on something that is either similar to belief propagation or belief propagation directly. And these recovery methods come with different properties. So first, the number of required inequalities that translates, for example, to the number of required faults or the number of required traces. Here, this is shown for Kyber 512 with all inequalities being correct. And the second important property is whether these key recovery methods are error tolerant or not. So that means if they fail, if we have incorrect inequalities in our set of inequalities, so we might not be able to use a side channel analysis or a fault that allows us to classify between decryption failures and decryption successes with 100% accuracy. So we want them to be error tolerant in the best case. And what currently know of none of these key recovery methods that have been used to offer are security estimates. So in case an attacker cannot retrieve a sufficient number of inequalities to perform a full key recovery, we currently don't know what the security level after such an attack is. So what we are currently missing is an error-tolerant key recovery method that requires only a minimum number of inequalities, a minimum information, and gives us security estimates. In different contexts, in general treatment of side channel information in LWE schemes, and also in the context of failure boosting attacks, often lattice reduction has been used. And of course, this is a standard tool for attacks on LWE schemes. And of course, if we could make use of the information we have from the LWE information we have in those schemes and these attacks, then we can potentially improve upon the key recovery. So this leads to the question of how can we combine belief propagation with the technique of lattice reduction. So the setting here that we have is, or that we assume, is that we first on the very left have an attack on a device, and this attack gives us inequalities as in the previous attack. So this could, for example, be one of the fault attacks or one of the side channel attacks, or any other attack that makes use of this strategy of introducing a small error using a chosen ciphertext, and then a side channel or a fault to observe the decryption failure, whether decryption failure happens or not. We modify this belief propagation from previous works to be error tolerant. So to achieve the error tolerance, we include this in the belief propagation. And of course, if the belief propagation directly gives us the secrets, then we are already done and nothing is left for us to do. But in all cases where the belief propagation does not allow us to directly solve for the secret key, we explain how the belief propagation output, how this statistical information can be integrated into a lattice problem, or rather how we can obtain an improved lattice problem from the public key equation and this information. This gives us a closest vector problem and then a shortest vector problem, and we can perform estimates for these. We can estimate the hardness, this is well known. And if we have the computational power available, of course, we can use lattice reduction to then finally obtain the secret key. So in the first step, we cared for the belief propagation and made it error tolerant. So the belief propagation in this case looks a bit like in LDPC codes, just that it's not low density, it's fully connected. And what we now have, we have check nodes in this belief propagation, and those represent inequalities. They perform Bayesian updating based on the inequality we obtain in an attack. And we add the property of correctness for an inequality to each of the check nodes. They can be different. So each inequality now has a property that is its correctness probability. And we consider this in the Bayesian updating we perform for each of the inequalities. These correctness probabilities, they're not a property of our method, but instead they're a property of the attack that our method is used for. So they could, for example, come from a fault reliability property, so a fault success rate, or the accuracy we get if we perform side channel analysis, and the accuracy with which we can classify the side channel information we obtain. So classify between decryption failures and decryption successes. The integration into a lattice problem then works in 2 steps. So we first run this belief propagation, and the belief propagation gives us statistical information on the key coefficients. And this works in 2 steps. In the first step, the attacker can usually infer the value of certain coefficients fully. So what we first do is we reduce the dimension using those fully recovered coefficients. And we do this directly on the LWE equation and in a way that respects the reliability information we have on all the other coefficients. So when we use one coefficient, we have a known value. We know the value of. We make sure to integrate it in a way such that it is optimal with respect to the information we have on the other coefficients. In the second step, we then embed into a closest vector problem, and this closest vector problem has a much closer vector compared to if we had just used the primal attack. So this is computationally more favorable. And in total, then this gives us the closest vector problem. And the first step here works directly on the LWE equation. So we do not immediately embed into lattice problem. Instead, we work on the LWE equation directly. And then only in a second step, we embed into a closest vector problem, which is computationally more favorable because we have a closer vector. This gives us a new key recovery method. This key recovery method achieves a lower number of inequalities for full key recovery. This is especially the case when we have incorrect information in our data set, in our inequalities. So in all the cases where we cannot determine whether decryption failure happened or not with high accuracy, we achieve error tolerance. So this is achieved by the belief propagation. And as we output a lattice problem from our key recovery method, we also get security estimates. Well, that means if we have, if you have 5,500 inequalities, then the security level is 0. But also if we have less inequalities than that, we get a security level, we get how much security is left in this instance of the scheme. We evaluate this recovery method in the context of the previous fault attack. So that means we used their simulation and subsequently used our key recovery method with the inequalities obtained in this attack. So this is also where the numbers are from, but as all these attacks recover the same kind of information, that really doesn't differ between the attacks. The security estimates are shown on this slide. On the y-axis, we have the security level in BKZ beta. That means the block size that an attacker needs to have after this attack to solve for the secret key. Higher block size means computationally more expensive. And on the x-axis, we have the number of inequalities that were retrieved in an attack. And we do this in several scenarios. 2 are shown here. In the first one, we have that all the inequalities are correct with a certain probability p. That means, for example, coming from a side channel. This could, for example, come from a side channel attack. And in the first sub-scenario, all inequalities are correct with probability 1. And in the second one, with 0.8, so 80% of the inequalities are being correct. And the second scenario comes from the previous fault attacks. There we have a fault success rate assumed. And this leads to a scenario where certain probabilities are correct with certain inequalities are correct with probability 1, and other inequalities are correct with a probability smaller than 1. And as you can see, in all cases, the security level drops quite a lot far before we can actually solve for the secret key using the belief propagation and also using lattice reduction. So the security level is greatly reduced far before we can solve for that. And a large-scale attacker can potentially carry out those attacks with much less inequalities than we on widely available hardware can. What can be seen in the figure is the two steps of integration. So we first have a rather slow decline in security. This is the embedding into a more computationally favorable lattice problem. And then at some point, the belief propagation starts to recover many values, many different values. Values are being fully recovered. This reduces the dimension. And this is where the steep drop after some amount of inequalities comes from. We also provide an information theoretic analysis. That means we analyze the theoretic content of information that is contained in such a linear system of linear inequalities. And yes. So in conclusion, we have several attacks and the whole attack strategy that work very very similar and target the error correction using a chosen ciphertext and then with a differing implementation attack afterwards. And all of these require key recovery from inequalities, from decryption failure inequalities. What we propose is to first use an error tolerant belief propagation. So first we use the statistical method that has been, similar attacks have used belief propagation in many other contexts. And what we then propose is integrating the output of the belief propagation into a lattice problem to make use of the standard tools we have in attacks on LWE. In this case, this gives us an error-tolerant key recovery that requires less information than we required previously with other methods. And we can output security estimates for the remaining security after having carried out such an attack. This is, for example, important if we have a countermeasure that, for example, shuts down the device after a certain amount of decryption failures has been seen. This is a countermeasure that has been discussed previously. So what our method does, it translates from obtained information to required computational power, gives us security estimates after we have carried out such an attack. And in addition, it reduces the number of inequalities. That means the number of faults or the number of side channel traces that an attacker requires. Thank you very much for your attention. And if you have any questions, please let me know.
Thank you very much for your presentation. We have a lot of time for questions. Are there any questions from the audience? Over here, please.
Yeah, I have one question. Are you actually implement the belief propagation?
Yes, we implemented the belief propagation. Is that the question?
Yeah, but you say belief propagation basically is an iteration algorithm. Then how many iterations you use?
That depends a bit.
For example, Kyber 512 case.
Yes, it depends very much on how many inequalities we have. So if we have a large amount of inequalities, then this terminates very quickly. Then it's, I think usually, I would have to look it up, but it's usually a small two-digit number of iterations. But if we have a very low number of inequalities, then usually we can abort after very few iterations because it's not going anywhere. But if we have something in the middle, then it takes a long time. But in general, this key recovery method, so except for the lattice reduction, of course, terminates if you have some reasonable computational power, then it terminates in a few minutes. And if you run it on an ordinary laptop, then it's maybe an hour or something.
Yeah, because you see, belief propagation method basically is decoding of method of LDPC code. However, in communications, LDPC code length possibly very low, less than 20. But in our case, in this case, the number of inequalities definitely more than 100. That's I was
Sorry,
guessing.
can you repeat the last part?
So I mean, in actual application of the belief propagation algorithm is in decoding LDPC code.
Yes.
However, the length of the LDPC code is very short.
Yes.
So, for example, in actual applications is less than 20.
Yes.
So, but in your case, it's very big.
Yeah, it's much larger and it's much more computationally expensive, but it's still in a reasonable amount because we can compute the updating in pretty optimized. So
Okay, thank you. If you can compute.
thank you.
Are there any other questions? Or are you all hungry for lunch? There's one question up front here.
Thank you for the talk. It was really nice. I would like to ask, does it work when we have to apply modular reduction on each inequality? Does this still work on that?
Probably, I mean, it depends a bit on the exact context, but probably not. So those inequalities are already integers, so they're not reduced modularly. I would assume that it.
Okay, so that means if we gather some inequalities and the number is, for example, overflowing the Q, that means we have this is not going to.
I think it depends on the exact inequalities you retrieve, but at least it's harder, yes.
Mm-hmm. Thank you.
Okay, last chance. More questions? If not, then let's thank the speaker again. So that concludes the session for the morning. We do have lunch now on second floor, and the afternoon session will start from 2:15. Enjoy your lunch.